to the last lecture,
Okay.
lecture 4, dynamic costs and budgets and examples.
Yeah.
Wait.
Okay, thank you very much, and thank you for coming. So this will be the last lecture. So before I proceed, I just want to tell you that I will update my previous lecture. I have some correction, and in particular concerning proposition 2. So indeed, I need to change this statement slightly, and it should be okay. And I will also correct maybe 2 types. Okay. Okay, in our previous 3 lectures, we always assume that every agent should have a sufficient budget to buy everything he wants to buy. But in reality, that assumption might not be true. So in this lecture, we are going to consider the assignment market, in which every household just wants to buy one house. However, they are having hard budgets, and they cannot pay anything above the budget. So it is possible that the budget might not be enough to buy things they want to buy. And this is quite a practical case. Now we want to design a dynamic mechanism which can still induce bidders to bid honestly, at the same time to allocate items as efficiently as possible. So that's the goal we want to achieve. So here we have actually 2 different types of private information. One is the budgets, the other one are the valuations. So in the sense, even probably you know that in contract series, if agents have say more than one-dimensional private information, then the design will become much more complicated, even in contract series. Okay, here we have a similar issue, and even in some senses more challenging issue. So here, because of a budget constraint, and the competitive equilibrium might not exist. So this is one difficult. Then the other one, so as I mentioned, we have 2 different types of private information. One is valuations, the other one is budgets. So this we have to overcome these 2 types of difficulties. Okay, so why that it's useful, it's meaningful to start the model with budget constraints. So I think in almost every society, most people cannot afford to buy big houses or send the kids to go to private schools, even if you you very much like to do so. So in the sense, we are actually most of the time are budget constrained. So and in most economic analysis, we simply assume that if you are a participant in a market, you value the house at $1 million US, you should be able to pay 1 million. And that's not actually, it's not the case in most cases. Okay. So now we have to think about this. And okay, budget constraint will become much more serious when you have a, say, financial crisis. The other sense is that like many organizations impose budget constraint to control spending. The other ones are salary caps are used by many professions to actually to reduce competition or relax competition. So and many other cases we also use budget constraint. Okay, and one thing why we do not think about a soft budget, because what is essential is about the hard budget. So soft budget means that or you might have you might not have enough money, but you can borrow something. Even if you can borrow, the amount you can borrow in most cases you have an upper limit. So in a sense, you still face a hard budget constraint. So this is therefore in most studies about the budget constraint, they consider about the hard budget. Soft budget is relatively easy to to deal with. Okay, so in this lecture, we are going to present an efficient and also incentive compatible dynamic auction for the assignments. Okay, and now what we can prove is that sensory bidding will be an exposed Nash equilibrium when both valuations and budgets are primary information. At the moment, we cannot prove that sensory bidding will be exposed to perfect Nash equilibrium. So, so we can only prove that when all agents are on the equilibrium path, off equilibrium path, we cannot prove the current design is not good enough for the more desirable case. So what the auction does, so achieve, so they can find an efficient outcome that is not only in the core, but also strongly priority efficient. When no bidder is budget constrained, then actually the auction found a valuation equilibrium with the minimum equilibrium prices. And we can also have a lattice result when you have a budget. And now this lattice structure is different from the assignment without budget constraint. Now this lattice can be open from below, but it's still closed from above. So this is a recent paper of me with my co-author Yi, just last month accepted by International Economic Review. Okay, we have a number of reference. So maybe I should mention 3 recent papers. One is by Gu and other 2 authors. They have a paper on Journal of Political Economy. They consider a quite general market, and the agent can demand several items, but they don't have a budget, and they can prove that under gross substitute preference, there exists a rotary valuation equilibrium. And then Bola, they also published the paper in Journal of Political Economy. We studied a very similar model, and actually they prove 2 different types of approximate valuation equilibrium. So in what sense? So the approximate valuation equilibrium, which allows some excess demand. And then the other case, so when the agents have a budget, and the other case is just the existence of a lottery of variation between allocations. Still, you have to allow excess demand. So when agents have no budget at all, and both results are under what they call debt substitutes. Basically, it's a generalization of growth substitutes. Yeah. So when delta is equal to 1, it's precisely growth substitutes. But delta can be more than 1, 2, 3. So and my paper with the same course, we consider actually a module markets that we have no restriction on the preference of every agent. And now the agents face a hard budget. In this market, we can we have a dynamic auction, which can always find a strongly priced or efficient co-allocation, and it can even find a strong co-allocation with a efficient assignment of atoms when new agents are budget constrained. So this is 3 new papers, but of course none of these papers discuss about the incentive issue. Okay. Okay. Now look at the model. So basically, it's assignment market. We already studied this in the first lecture. So we have n atoms, and we also use 0 to mean the dummy atom. Now we have a group of bidders, n. Then I use 0 to represent the seller. Okay, now I still use integer values because now I have a dynamic auction. The increment, the unit of adjustment is just 1 unit. 1 unit. Therefore, I use this integer value. Okay, every bidder H is associated with a hard budget DH. It means you cannot have anything above this budget. Okay, so now we, for easy posing, I assume that the reserve price of the seller for on every atom is 0. This okay. Now I already mentioned in the beginning why it's essential to consider hard budget, because even if you have a soft budget, you can always, in the end, you end up with a so-called hard budget case. Now, so what we mean, a bidder is budget constrained. It is the case when his budget is below the value of some atom. So it means that you have a valuation on some house which is about to say 1 million, but actually your budget just 500,000. So this is if you have such scenario, then you are budget constrained. Otherwise, the bidder, if you can always pay up to your valuation for any atom, then you are not budget constrained. This is and then I have to stress this factor. Actually, there's some confusion in the literature. Actually, many models also take budget into consideration, most cases, actually, there's an underlying assumption agents are not budget constrained. So that's quite important to point out. Okay, now we make two assumptions. So one is about private information on valuations and also on budget. So everyone's knows his valuation and also his budget privately, and the agent can be strategic. Okay, cost linear utility. So here, okay, so if the agent is bidder, and he will get this payoff, and the seller will get the payment if the item is sold to this bidder and at prices PA. Okay, so here you see this assumption is also very different if you are familiar with literature about budget constraint. This is a very large one, so we don't impose that the condition that when you have a price above your budget, then you your utility will become minus infinity. So in order to avoid that case, we will have a punishment in the auction design. So but for the utility, so why this assumption is reasonable? For instance, if I have a valuation on the house is 1 million, and my price my budget is 500,000, and if I pay 600,000, that my payoff still 400,000. That's the idea. Although I cannot pay, but for my payoff, it's that should be still true. Now, how can we avoid that the price goes beyond my budget? That will be the issue of design. So this is something I want to say. Okay, then we have, okay, this is just a refreshment. That the assignment, so it's just a redistribution of atoms among all agents in such a way no real atom should be assigned to more than one agent. And it's possible some agents might not get any atom, in that case, get the dominant atom. And it's possible some real atom might not be sold, then those atoms should be kept by the seller. Okay, then we use this calligraph A to denote the family of all assignments. Then we will have this efficient assignment, which achieves the highest market value. Yeah.
So can you help me a little bit? So I guess you have a setting in which there's a budget constraint.
Yes.
So is it still reasonable to define the efficiency in this way that the you need to maximize the sum of the variations? Because suppose that some are zero budget, then
As a
that would be reasonable to consider that as an alternative allocation to be.
yes. So I will come to you that point. Actually, in many cases, this will not be achievable.
Okay.
Yeah. So we have to actually now you see we have although we have a transferable utility, but when you have a budget constraint, then it will become a non-transferable utility.
Yeah.
So it becomes an NTU game. Yeah. So this is something changing quite dramatically. Yeah. Okay, now here we have a payment or transfer vector. If it's a if all payment is less than or equal to the budget of every agent, then we see this payment is feasible. And now we use T0, which is the sum of all payments. This is the seller's revenue. Okay, then a pair, say assignment and a feasible payment T is called an allocation. Okay, then at this allocation, so then this is the utility of the bidder. So the object he gets, this is the utility minus the payment. Okay, then what the seller can get is the total payment. Okay, now now we have a competitive equilibrium. So now, okay, for each item, we give a price. Then for the dummy, price will be always 0. And then, okay, we have to define the affordable, the set of affordable items, any items which is the price you pay is below your budget, then it's it's fine. So then you try to maximize your surplus for all affordable items you compare. Okay, so here and here we use this set of affordable items under your budget. Then we have the valuation equilibrium. So the valuation equilibrium, you have a price vector and the assignment. Then you have okay, everyone gets an optimal bundle, and for any unsold item, the price should be equal to 0. So okay, now we will actually we can easily have situations there's low competitive equilibrium. So firstly, we consider very simple case. One item, 2 agents, and both agents have equal budgets. B1, B2 equal to 6, and the value of bidder 1 is 20, the value of second one is 18. Then there's no valuation equilibrium price, because at 6 both want to have the item, and there's a over demand. And but if you increase price, then it's beyond your budget, so it's not possible for you. And here, so this is basically because the item is indivisible, and the bidders are budget constraints. It means some utilities cannot be transferred from one agent to other. If this is not the case, actually we have a competitive equilibrium. So if the bidders are not budget constrained, then so it means that for agent 1, your budget should be no less than 20, right? And for agent 2, your budget should be no less than 18. So then you can always increase the price up to 18 and then slightly above, then the bidder 2 will get the item. You have a valuation equilibrium, right? And the other case, if the item is divisible, then each of us just get half. Then we pay the same price, 6. It's an equilibrium. So here you see 2 factors play a role. One is indivisibilities. The other one is budget constraints. Okay, so this, okay, so this is a very particular case, the equal budget. We can also easily have a more general case that agents have different budgets, and we can still have a difficult. So now here, seller has two items, A1, A2. Now we have three bidders. And now for this example, the bidder one is not budget constrained because his budget is above his valuations. But bidder 2 and bidder 3 are budget constrained. Okay, and for this market, there's no variation equilibrium because in order to have equilibrium, you need to have a price for A1 should be no less than 5, and price A2 should be no less than should be no less than 3. However, when the price is a little bit change, then what happens? So you D2 will have an empty and just done good, and this one will have you don't want to have the atom anymore. So there's a low price to balance the demand and supply for one atom. So there's no variation equilibrium in this example. Yeah, so then this so we have to use more general concept of general solution for this problem. And one thing is about we use core. Okay, so then we first have a allocation is individually rational if his utility, if everyone's utility is greater than or equal to 0. So it's better than it should not be worse than the case you stand alone. Okay, then because we consider the concept of the core, then we have to think about what should be the right correlation. So here I subset a empty subset of agents, so include the seller and the bidders. Okay, what we call a variable correlation. If the S, the set, the correlation consists of the set, either seller with any number of bidders or a single bidder. So we don't need to consider a correlation of several bidders because they do not have any effect. But we need to consider individual bidder. And the only correlation matters is that you have the seller and also the bidder. And that's quite crucial correlations. So we call this what we call a variable correlation. So just restrict the number of correlations, and because other correlations beyond this has no effect. Okay, given a variable correlation, so then we need to define what will be a blocking correlation. So you just try to define what is the core or strong core. So correlation, allocation rho S and pole is feasible for the correlation S. If in the first case, so if the correlation contains the seller, and then the payment for every member in the correlation, every bidder in the correlation is less than or equal to his payment, and any other non-correlation member, then they should get a low atom, and the payment should be 0. Okay, then the other case just the correlation contains a single bidder, and that single bidder, when he stands alone, then the payment is 0, then he gets no atom, just W atom. So this is we give a definition of allocation for every variable correlation. Okay,
But
sorry.
one question, so here, so in the case that S consists of a single bidder,
Mhm.
so then okay, so the blocking by the single bidder is different from individual rationality for
Actually, the blocking will be the same.
blocking will be the same.
Yeah.
Oh, I see.
Yeah, because so blocking you mean so I will next slide we will come to that point. Yeah. Okay, so then we define blocking and call also strong call. So here allocation pi t is blocked by a variable correlation S if there exists a feasible allocation for the correlation S, such that okay, every member in every correlation member should become better off, strictly better off when they are in the correlation and compare with the original allocation. Okay, then this is a block, and then we also have a weak version of blocking. So is weakly blocked if okay this is greater than or equal to for all correlation members, correlation members, and with at least one member should become strictly bit off. So that's the definition of two types of blockings. Then the core, I think most of you are familiar. Your allocation pi t is in the core. We call a core allocation if it's not blocked by any variable correlation. But it should be variable correlation. Or correlation should be okay. Yeah. Because I think it's better to use a variable correlation. This is okay because I define this. Yeah, it's okay. Okay,
So
yeah.
I have an impression that this definition does not reduce to the Eurasian equilibrium, even if there's no budget constraint. And is that true?
No, this one it's possible. The second one, the first one, like strong core.
I think the strong core is actually sort of induces the Eurasian equilibrium outcome.
Yeah. So yeah, in a strong core case, then we can prove that such an allocation, if we have a result that when the agents are not budget constrained, then it will find a strong core, and that strong core will be actually the variation equilibrium with the minimum variation price vector. Yeah.
Oh, sorry. Actually, my question is, so you seem to be saying that your auction finds a point in the strong core, and then in
No, so the auction will find a strong core allocation if no bidders are budget constrained.
okay.
And in other case, the auction will find a core allocation, which is strongly priority efficient.
Okay, I see.
Yeah.
But my question is different, actually.
Yeah.
So my question is, I thought that your motivation seems to be that with budget constraint, the Eurasian kingdom does not always exist.
That's true.
Right. So I was hoping that your core notions will induce the outcome that is Eurasian kingdom allocation if there were no budget constraints.
No.
That implication is not-
No, if there's no equilibrium, no variation equilibrium, we cannot get anything.
No. My question is
Okay.
So my question is much simpler actually. So am I right that without the budget constraint, it is not generally true that the strong core allocation is always very giant allocation?
I think it is equal. That's separation.
It is?
Because we are talking.
Yeah.
Yeah.
Are you sure? Because I thought that you are defining the blocking in a slightly different manner.
I saw. So I wasn't paying attention.
No.
Okay.
This is okay. This one is okay. Not is the first one. First one.
Maybe I'm really confused, sorry, but didn't you define the blocking in such a way that all the
So actually,
position includes the entire sort of like sellers all the goods together, right?
Yes.
So that seems to mean that the seller could have that there could be a core allocation in which the seller somehow, let's say, uses some goods to be allocated or with something like a high price.
You could have a situation that the seller may maximize its revenue, but in that case could be very bad for the bidder. That's possible. But the other case is that it could have a minimum equilibrium price vectors, which is good for the bidder. Sorry. So we actually later on we will come to that result. So basically, the auction will find a core allocation which is also strongly priority efficient if bidders are budget constrained. If the bidders are not budget constrained, then this auction will find a variation equilibrium with the minimum variation price vector. So that's the result we will have.
The questions.
Yeah.
So are you going to show that strong core always exists even under budget constraint?
Strong core, no.
So what happens to your auction if there is no strong core?
But the core exists.
As a core, so the statement is core always exists.
Yes, yeah. So actually, this is in some sense, very similar to Shapley scarf model. So over there, they prove that they exist in a core. However, when you have a indifferent preference, you cannot have a strong core. Yeah. So, yeah.
Does the variable have spike?
Yeah,
Or-
I don't need to consider any correlation which just consists of bidders because you cannot do anything. So I don't need to.
So, okay, I see. So if we remove variable, it doesn't change anything.
No.
So, okay.
No. Just restrict the number of cases. Yeah. Okay. So then now let me introduce the auction. So the basic idea is that in the first round auction, on every item bidders first makes a bid or no bid at all. So it just then the seller will choose a set of bidders, set of bids which generates the highest revenue for for herself, and then asks every provisionally loose bidder to make a new bid. We will come to define what we mean provisionally loose bidder. Then in every subsequent step, so every provisionally loose bidder will make new bids, and the seller again will choose an optimal bids which maximize her revenue. Then this process continues until no bids will be made. So then we also want want to avoid overbidding or manipulations. So first now, if the price goes too high, then we will actually punish such behavior. So let's put this price gap omega star, which is a significantly, considerably bigger than the number of bidders times the number of items. You can imagine the valuations and the budgets for this kind of, or so just make a huge number, choose a huge number. If the price goes to that level, then you punish those people. Okay, now let's look at the auction in detail. So the first step on every item, so includes the dummy. So every bidder makes a bid, just choose a integer price you are willing to pay, or you indicate you don't want to do anything, you don't want to bid, that's fine. Then we go to the provisional assignment stage. Then the other, the bidding stage. So after being offered to make a new bid, then actually every provincial loose bidder will increase some of his previous bids by 1 unit, or makes bids upon some items which they have never made bid before. Okay, in this one, so bidder must increase one of his previous bids, or make a bid on an item which he has not yet made bid before. Okay, now here, any other bidder which is not provincial loose bidder, just keep the bids unchanged. Okay, now we go to the Lexus. Yes, sorry. Yeah, sure.
Can you remind me who are the provisionally?
Yeah, I will come to that point.
So in the initial stage, who are they?
Are
they
no. In the first stage, there's a low provincial loose bidder. Yeah.
So at this point, you have not.
No. Okay, now let's go to the next stage. Then we will introduce what we mean by provincial losing bidder. So here, the provincial assignment stage. So if bidder has not yet made a bid on the dummy item, we see this bidder is active. So this means that currently you are not actually interested on the dummy item. This means you still can make a positive surplus for other items, basically, it means. And then, then this the auctioneer will set the price of this agent on the dummy atom, so the minus to the power minus h. So this is a kind of a tie-breaking rule we designed. Otherwise, the bidder is inactive. So inactive, it means you actually made a bid on the dummy atom. And in this case, the price of the dummy atom must be set to at zero. Okay. And what other things the auctioneer will do? So if a bidder H has not yet made any bid upon any real atom until the current stage, then we set an artificial price for that atom. So simply minus infinity. So minus infinity, why we use this one? It means that when the auction, sorry. Wait, sorry, I make a mistake. Sorry. So why we use this minus infinity? Simply, it's when the auctioneer will choose the seller or seller auctioneer, we treat it in the same way. So for this one, minus infinity, this means that when this seller tries to find a set of bids which maximize the seller's revenue, then you will level choose the bundle, the items that the bidder has level bid to that bid. So that's the intuition. And then, okay, so now we get such a price system. So if at any stage, if the price of some items goes very far, so actually equals to the cap, then actually we will assign this item to the bidder, and he will be punished. Otherwise, if this is not the case, then the seller or the auctioneer will just choose a set of bids which maximize the seller's revenue. Okay, now we come to what we mean a provisional loose bidder. So if this bidder is active, namely he has level bid on the dummy atom, but now he is assigned the dummy atom. So it means that actually this bidder has bid something else, but the auctioneer does not assign his bid items, means that if that does not give the seller the highest revenue. So then what this auctioneer does is that the auctioneer will simply assign a dummy item to such a active bidder. So this one, this is the intuition. So someone who still can make a positive surplus, but at current stage, his bids are not chosen by the seller. So this means that this bidder will be still able to make new bid. This is the intuition. So suppose now I made a bid on number of items. After this, the auctioneer choose which bids the seller wants to have. However, my bids are not accepted by the seller, and so in the sense I'm temporarily assigned to the dummy item. Okay, so that's because I can still make a positive surplus. Therefore, I still have an incentive to make new bid. This is the idea. Okay, so if there's no provincial loose bidder, then the auction will stop. Otherwise, then the seller will ask all provincial loose bidder to submit new bids in the next round. So that's the auction. Now, okay, the final assignment. So the auction ends at some state K. Okay, then every bidder will get a item. So from the currently choosing assignment by the auctioneer. Okay, if he can pay his current bid, otherwise, and he will not get the item, but pay penalty if he cannot pay his bid. So means that his bid exceeds his budget, then he will be punished to pay this debt. Stop. Okay, then the other case is that the bid of some bidder goes to very high price, the cap that omega star, then this bidder actually will have to pay that price, but of course he cannot pay. So he will get nothing, and for others he will get nothing or pay nothing. But this one, he will have to pay this price. But in some sense, he cannot pay this price, but we can still give him a penalty. So this is the option. Now we need to specify what is the sincere bidding strategies. This now we have to. Okay, I already mentioned here. Okay, now let's look at some properties. So here, the auction has a very specific rule, in particular on the dummy item. So the auctioneer actually does not allow the seller make price on the dummy item. So you just need to indicate whether you want to have this dummy item or not. So if he's active, then the price will be set by the auctioneer by this number. Otherwise, the price will be set at 0. So this is a rule. And then it's important that here we need to differentiate active bidders and inactive bidders. So this is a kind of a tie-breaking rule. Okay, so actually this rule also improves market efficiency in a sense that if beta H has bit on the dominant atom, and now this beta is indifferent between the dominant atom, possibly some other real atoms, then actually this auctioneer can give other beta priorities to get real atoms so that this will not hurt this beta H. So this rule is quite interesting. So in some sense, it can also improve market efficiency. Now let's look at what lemma we have. So if beta H is provincially losing beta in an optimal assignment for this problem, now in the auction provincial assignment stage, we have the auctioneer solve this problem. So then this beta must be also assigned a dominant atom in every other optimal assignment row of the problem. So in a sense that this problem one has a unique set of provincially losing betas. So this gives you a nice property. Okay, let's look at how we define the sensory bidding strategies. So actually, we try to mimic the behavior of the seller in the English auction. So in the first step, that every bidder sets a attainable utility. That so the attainable utility, then we will update this according to the which stage he is. So the first step, okay, the possible attainable utility is that the maximum value of every bidder on all atoms. So this one. But then in the auction process, this attainable utility will be actually adjusted, actually will be gradually decreased, because your first target probably like students apply universities. First you submit your application to Tokyo, and then too high, then you will be rejected, and you gradually to say, okay, to other university. This is something very similar. Okay, here, for any step which is goes beyond the first step, if the bidder H is a provincial loose bidder, then he will make new bid by reducing his attainable utility by this amount. How much is this amount? You look at, so this is the previous, this is the attainable utility in your previous step. Then you try to reduce your attainable utility by 1, by 2, up to, so as long as this payment will be still in your physical domain. We here physical payment. Of course, here we only talk about the integers, positive integers, and then we take the minimum. So this D, now you consider actually any atoms which you can possibly choose, and that now you reduce this attainable utility, and this delta K actually is the minimum integer to make this change happen. So in most cases, this delta k is 1. But when when the bid of this loose bidder reaches on some items reaches the budget, then this delta k can be larger than 1. So we will later on we will show you some examples. Okay, when we define in this way, then how the bidder will update the price, they will do in such a way. So for each step, for every item, that every provincial loose bidder calculates a possible price. So this is the your valuation on the item A, that minus your current attainable utility. Then you decide to make a bid or not at all. So in the first case, if your current price is still affordable, so namely in between 0 and your budget, okay, this is okay, you just take it. Otherwise, if this utility, this price is above your budget, then you cannot pay more than your budget, then you just okay, set this price at your budget. Okay, then the other case, so actually you don't you don't want to bid this item because the profit is negative, so you don't want to bid this item. So I use a star. Okay.
So
Yeah.
in the first stage, k equals to 1, you have is the maximum utility. So
Yeah.
there are 10 houses, and the best one,
Yeah.
okay, its value is million. So p hat is 0 for
Yeah.
my best house,
Yeah.
and negative for all other cases.
Yeah.
So in the first stage, I propose 0 price for my best house, and
Now you
star
put-
for-
Yeah, then you gradually increase your price.
and what is star?
Star just means that you don't bid on the item. Yeah, just a simple, just a.
Item A includes a dummy item.
Yes, yeah.
So in the first stage, I propose 0 to my best house, and I don't bid anything to any other. So
Yeah.
that's what happens in the first.
Yeah. So we will have such a scenario. Okay, so this is the sincerely bidding strategies. Okay, let's look at one example. This is a little bit more complicated than the previous two, make the example more interesting. So now here you have 4 bidders, and now all agents are budget constrained. Now let's look at how demand scale Sotomayor auction work for this example. So let's look at this auction for
So this is without budget constraint.
with budget constraint now. So I directly use demand scale Sotomayor.
Okay.
Yeah, so now let's see what will happen when you apply the DGS option. So this SK is I use the minimum of demand set. So you see here, first one you have A1 is a minimum of demand set. Then then the other cases you have actually 2, right? 1 is the minimum of demand set. and 2 is also minimum of demand set. So I speed up so that I have this scenario. Now,
Like a simple question.
Yeah.
The reason why you are showing this is to show that your auction reduces to DGS in this particular example,
no.
or DGS doesn't work.
That's
What
right.
you-
Yeah.
I see.
Yeah. I will show you.
DGS doesn't work. but-
Yeah. So here, actually, not only DGS, also Booster Caddy, Osbear, and my auction, previous auctions also. If you apply directly, there's a problem, namely, because in those auctions, typically the seller offers the prices, and then bidders respond, right? Bidder responds. So in this sense, that the auctioneer cannot properly adjust price. So that's so when the bidders have a hard budget or when bidders are budget constrained, then in those auction process, you will have a discontinuity in demand. So now I will show you this one. So just take, I don't mean to criticize the auction, just means just want to show that why they don't work.
I see.
Yeah. So here you can see that from you see here, bidder 4 actually has a jump in demand from step 5 to step 6. So bidder 4, you see here, there's no continuity at all. And then actually bidders 1 and 2 also have a jump in demand from 6 to 7. So in the end, you have this you reach this state, and the auction will stop. And in this case, the total increase of utility from the trade just 7, namely you you assign item 2 to bidder 3, then item 1 will be kept by the seller, and then the total utility of the trade is 7. Okay, now let's look at what happened for the new auction. So what for this the purpose of this example by using DGS is to show that there's a when there's a when bidders are budget constrained, there's a discontinuity in demand if we use like the typical DGS auction or Osbear Goose Staccato. Also myself, my own auctions doesn't work because over there we cannot maintain the continuity in demand. And here, for this example, we have the sorry. So for this example, now the total utility from trade is 7. Now we will compare the new auction. Okay, so here let's look at how the new dynamic auction works. So the first step, we calculate the attainable utility for every bidder. So you have a 10, 10, 7, 7. So let me, I should have a print some. So 10, 10, and 7, 7. So the maximum attainable utility. Okay, that okay. So actually, so this means that the price, the bid of bidder one. This is for the dummy. He is active, and he bid. He offered the price of 0 to atom 1, and this one he does not bid on atom 2. Okay, the same for bidder 2. So he is active, and he bids atom 1, does not bid on atom 2. Okay, etc. Now here, actually for bidder 2, no, bidder 4, sorry. Bidder 4 is different. Bidder 4 actually offer prices to atom 1, atom 2, both at 0. Now what the auctioneer does, just choose a one which maximize its revenue, but now according to these numbers. So then you choose to assign A1 to bidder 1 and A2 to bidder 3. This will be the maximum one. So include the minus sign because this plus this is the minimum one. Okay, so now here we have now here you see only bidder 2 and bidder 4 are provincial loose bidders, right? Because they are assigned the dummy atom, but they didn't demand the dummy atom, right? So by definition, bidder 2 and bidder 4 are provincial losing bidders because they did not bid on the dummy atom yet. They are assigned the dummy atom. Okay, that's important because otherwise we.
So if you conduct the DGS in the previous slide,
Yeah.
in the end, you get Walesian equilibrium.
No, that's not an evaluation.
You have excess supply.
Yeah.
Okay.
Yeah.
I think you can make the same point by much simpler example where originally you showed us one item case, 2 bidders, same budget of 6, and they have a value of 8 and 10.
Yeah.
If you do, Gale demonstrator here, if price is below 6, there is excess demand.
Yes.
At the 6, still excess demand.
Yeah.
So price jumps from 6 to 7. And that's the end of the process.
Yes.
And demand is 0, and the
Yeah.
items are not allocated.
Yeah.
And if you apply your thing to that example, so at price 6, winner is chosen according to this type rating.
Yes. That's still yeah.
So it's not the case that a person who has the higher value gets the object.
Not necessarily.
I see.
Not necessarily because in the first case, either of the two could be chosen. But now we have an order. Then you will.
Those two people have different. You had.
Yeah,
Starting point is different. So somehow I thought that your auction
we
highest.
we have sorry we have this one. We have this this will differentiate them. Yeah. So okay. So here you see that these two bidders, bidder 2 and bidder 4, are provincial loose bidder, so they will be offered new opportunities to make new bid. So you see they will decrease, you see, decrease the bid. And this is 10 to 9 and 7 to 6. So so you see the increase, the bid, and also this increase the bid to both. Okay, then we have this now they change the assignment. Now you then you have another situation. Then just repeat this process. What we get. Let me show you. So here there's one thing I need to mention. So in step 7, there's a jump. Okay, here you see from 7 to 8, there's a huge decrease of attainable utility for beta 4, from which drops from 4 to 0. And you see the other cases are all just 1 unit. So there's because here they already reach the budget, and there's a big jump. Okay, now let's look at how the auction ends. So actually, in the end, the auction will stop at step 17. Now you have this final assignment, and there's no provincial losing bidder anymore. So then the auction stops. Then actually here you can see that the item 1 should be assigned to bidder 1, and item 2 will be assigned to bidder 3. And in this way, actually the trade has improved quite a lot. So from 7 to 17. So that you can see this change. Okay, so this clear? Okay, so let's we have equilibrium. So sincere bidding will be exposed in Nash equilibrium. So let's look at what we have. Several theorems. So we have the proposed auction terminates within a finite number of steps. Just regardless, whatever bidders do, this auction will always end in a finite number of steps. That's very easy because it requires that you need to change at least 1 bid. Okay, then this one, so this theorem says that sincere bidding is exposed Nash equilibrium of the dynamic auction game. So this result, in some sense, generalize the result of Maynard and demand theorem. So so actually we try to design a more desirable one, that in order to achieve exposed profit Nash equilibrium, but that's too difficult. So we can only get this ascending auction. But the ascending auction, if you make a mistake, and it might end up non-core allocation. So then therefore we cannot use exposed profit Nash equilibrium, because we cannot have off equilibrium pass results. Okay, then we have another theorem. The proposed auction found a strongly Pareto efficient core allocation, and this the third one. So very interesting one. Very interesting. If there exists a valuation equilibrium the price vector found by the proposed auction is not larger than the minimum integer valuation equivalent price vectors. So in the sense that the prices found by the auction quite favor the bidders. In some sense, this is the reason why it's a strategy proof for the bidders. Okay, then the other results. So when no bidder is budget constrained, then the proposals auctions found a valuation equivalent with the minimum equivalent price vector, which is also in the strong core. This okay, then the
Question about theorem two. Okay, so in more general model with quasi-linear preferences,
Yeah.
individual goods, and quasi-linear preferences, individual goods, but budget constraint. What about what do you know about the existence of a core in such an economy? Quasi-linear, individual goods, but budget constraint.
yeah, this is a
No, this is assignment case. We are talking about assignment case. Each buyer can.
oh, you mean the general one?
General one, yeah.
Oh, okay.
What do you?
Oh, in general, right, so we have a paper just mentioned at the beginning. So actually, we can have a very general one that there's a low restriction on preference.
Mhm.
So if bidders are budget constrained,
Mhm.
then you can we have a dynamic auction which can find a co-allocation, and this co-allocation is also strongly Pareto efficient. This
So in the general model, core always exists.
Yeah. And also, if there's no budget constraints, if no bidders are budget constrained, then actually we can find a strong co-allocation. Yeah. Okay, I think then we have another theorem. So if a valuation equivalent exists, then actually the set of price vectors, valuation equivalent price vectors forms a non-empty lattice, contains a unique minimum integer valuation equivalent price vector, and also unique maximum integer valuation equivalent price vectors. But they could be equivalent prices which are not integer but are below this minimum integer equivalent price vector. And so that's the something like this example, very simple one. You have this which is open from below. So this is the example. Okay, so well, we have maybe two open questions. One is whether it's possible to design a dynamic auction for this, just for this assignment, so that sincere bidding is exposed to perfect equivalent, or even a dominant strategies for all bidders. This is quite challenging. Then the second one, whether it's possible to design a more general auction for substitutes case. It's not easy. It's when bidders are budget constrained, but have a gross substitutes preference. So I think I stop here. Any questions? Thank you for your attention and for your comments. And I think I will update my previous lecture 3. There's some correction. This one so far so good. I don't find any mistake. Good.
Okay, so any questions or comments? Okay, then let's thank the speaker.
Thank you.